So today we're talking about the inverse of a function. So the way that we're going to find the inverse is we are going to flip the x and the y, and then we're just going to solve for y. So remember that f of x, that stands for your y, right? So this would be where y is at. I have x here, and what I'm going to do is I'm going to flip those. So the x is going to be where my y is, and the y is going to be where my x is. Now, I did not move anything else. I only changed where the x is located and where the y is located. Notice, I did not take the 3 and move it with the x. You're just going to change locations. You don't change anything else. Then you're going to solve for that y. So I need to add the 1. So now I have x plus 1 is equal to 3y. And then, since I'm multiplying this y by 3, I'm going to divide by 3. Now, if both of these terms will divide by whatever number you're dividing by, you should go ahead and divide them. But ours do not, so I just end up with y is equal to x plus 1 over 3. Now, I need a way to show that this is the inverse and not my original function. So we are going to use inverse function notation, which is I'm just going to take this f of x, and I'm going to put a little -1 up kind of where the exponent would be, and that's going to represent the inverse. So I'm pretty much just stating this is the inverse of this. So this was g of x, and this would be g inverse of x. And there you have it. All right, so on number 2, first thing I'm going to do, switch the x and the y. So I have x is equal to 1/3, put a y in place of the x, minus 2. And then I'm going to solve for this y. So I'm going to add 2. X plus 2 is equal to 1/3 y. And then I need to get rid of this 1/3, but instead of dividing by that fraction, I will multiply by the reciprocal. But I have to realize that I'm multiplying this entire side by 3, so you want to enclose that in parentheses so that you don't forget. So I get y is equal to, and then I'm going to distribute this 3. 3 times x is 3x, and 3 times 2 is 6. And then I need to use my inverse function notation. So f inverse of x is equal to 3x plus 6. Now, you can cut an entire step out of writing. If you already realize that y is going to be by itself, you can go ahead and at that point plug in your f inverse of x and replace that y. All right, so on number 3, we're going to go ahead and flip and do x is equal to -y plus 1. Notice I did not move that negative. It is still in that same spot. And then I'm just going to go ahead and subtract the 1. So I have x minus 1 is equal to -y. And then I need to get rid of the negative, so I will divide by -1. And both of these terms divide evenly by -1, so I'm going to go ahead and divide that out. Y is already going to be by itself now, so I'm going to go ahead and replace it with f inverse of x. That saves me a step of writing. So x divided by -1 is -x, and -1 divided by -1 is +1. So first we're going to find the inverse, and then we're going to graph the function and its inverse on our graphing calculator. Notice this has a little extra piece of information, which we'll talk about in just a minute. So we're going to kind of ignore it for the time being and go ahead and find the inverse of the x squared. So I'm going to go ahead and flip the x and the y, and then I'll solve for y by taking the square root. Now remember, when you square root or even root anything, you must have a positive and a negative answer. So I have y is equal to plus or minus the square root of x. And I could have at that point went ahead and done my inverse notation. I just failed to notice. So f inverse of x is equal to plus or minus the square root of x. So we've stated that x has to be greater than or equal to 0 because we want to avoid those negatives underneath our square root. So this is our inverse, and we're going to take and graph both of these together on in our graphing calculator. All right, so we've put one of them in the y1, another one in the y2, got our plus or minus in front of our root here. And then this is going to represent what I'm going to call the mirror, okay? An inverse is going to create a mirror with its original, right? So when I press graph, all right, notice here is my original, here is my inverse, and here is my mirror. Now I'm going to zoom in on this just so you can kind of see. Oops, might help if I actually put zoom in. All right, this graph should mirror onto the other graph. Are you with me? So think of this as your mirror. Think of this as you, and this is your reflection, right? So that mirrors over onto this red one. Notice this red mirrors over onto the blue. This blue mirrors over to the red. Now, because this is not evenly spaced, right, it might look a little funky. I'm going to show you here later on in the lesson how you can be definitely sure that you are correct. I also want to point out that where my red graph and my blue graph intersect, my mirror cuts right through those intersections, right? So that is also a good indication that you have done a good job, all right? All right, so on number 5, we're going to start off switching the x and the y. And then we're going to solve for the y. So I'm going to subtract the 4. So I have x minus 4 is equal to negative y to the third. And then I need to get rid of this negative that's being multiplied. All right, so I'm going to divide by negative 1. And I'm going to go ahead and simplify that because they'll both divide evenly by negative 1. And I'm going to go ahead and put my y cubed on the left. So I've got y cubed is equal to negative x and then a positive 4. Then I'm going to go ahead and cube root to get rid of that cube right there. And remember, when you have an odd root, you don't have to do the positive and the negative. So y will be by itself. I'm going to go ahead and use my inverse function notation. So f inverse of x is equal to the cubed root of negative x plus 4. And then we're going to go ahead and graph that so we can take a look and make sure that we've done a good job finding the inverse. All right, so we have our original, we have what we found to be our inverse, and then we have our mirror here. We're going to go ahead and graph it and just make sure we've done a good job. So if you look, this blue would lay over and mirror on top of the red. Same thing here. So it looks like we've done a good job on that one as well. All right, so if you will recall from Algebra 1, if we had a graph of something, we could do a vertical line test, and as long as that vertical line only intersected at one point, right, that means that it was a function, okay? Well, if you do a horizontal line test, you can tell if its inverse is a function. So the inverse of this would not be a function because it would touch our graph 2 times. And we already graphed the inverse of something that looks like this. It looked like this, right? And if you did a vertical line test, it would not be a function. So the horizontal line test is just if you have a picture of a graph and you do a horizontal line test, you'll know if its inverse is a function or not. So we're not actually going to do that. That's just information that I stuck in here for us. So what we're going to do is we're actually going to do this backwards. We're going to find the inverse, and then we're going to determine if the inverse is a function. So let's switch the x and the y. So I have x is equal to 2y to the third plus 1. And then I'm going to go ahead and solve for y, so I'll subtract 1. Which gives me x minus 1 is equal to 2y to the third. Then I need to get rid of this 2 that I'm multiplying by, so I will divide. And I know over here that x and this negative 1 do not divide evenly by 2, so I'm going to go ahead and just leave that as is. So now I have y to the third is equal to x minus 1 over 2. And then I'll get rid of that cube by cube rooting. So now my y is by itself. I will use my inverse function notation. And I have the cubed root of x minus 1 over 2. All right, so now we're going to go ahead and graph both of these and determine if the inverse was a function. So we have our original, we have our inverse, and we have our mirror. So the blue represents our original one. This represents our inverse. So is the inverse a function? Yes, the vertical line test would tell us that. If we did the horizontal line test on the original, that would also tell us that that is a function. And it looks like we did a great job finding the inverse as well, because it does make a mirror across. On number 7, we're going to go ahead and flip x and y. And if you've already been paying attention, you already know that this is also a cubic function. They're going to look exactly the same. So if we were to graph these, it would have the same shape. So it would definitely be an inverse. We're going to go ahead and find the inverse, though. So we're going to add 2. So I have x plus 2 is equal to 3y to the third. And then I'm going to go ahead and divide by 3. X plus 2, that does not divide evenly by 3, so I'm going to just leave it like that. So I have y cubed is equal to x plus 2 over 3. And then to get rid of my cube, I will cube root. And now that I've got y isolated, I can change it to inverse function notation. So this would be the cubed root of x plus 2 over 3. And again, it's going to look almost exactly like the last one, just kind of in a different location. All right, so flip your x and your y. All right, so we're trying to gain access to y right here, which is under this square root, but we still have something outside of that. So I'm going to go ahead and divide by the 2. So I have x over 2 is equal to the square root of y minus 3. And then to gain access inside that square root, I'm going to have to square both sides. Now, make sure that you're squaring the entire side and not leaving part of it off. So that will cancel on this side. X to the second power is x squared, and 2 to the second power is 4. And then the last thing I'll do is add 3. So now that I have y isolated, I'll use my inverse notation. So f inverse of x is equal to x squared over 4 plus 3. And again, you could graph that to tell whether it's an inverse or whether it's a function or not. So there are multiple ways that we could take two functions and tell if they're inverses or not. One way would be that you could just take one of them, find the inverse, and if it was the other one, then they're inverses, right? The second way is you can graph them and take a look at them. The third way is something that we've already done. You just didn't really know how else it could be used. So what we're going to do it by hand, then we'll do it in the calculator. We are going to do a composition. So we're going to take the g of x and we're going to plug it into the f. And then we're going to do the same thing, but we're going to do it backwards. We're going to plug the f of x into the g of x. So I'm going to start with this one first. I'm going to take g and I'm going to plug it into f. So I'll take f of x, and wherever I have an x, I'm going to put a big parenthesis there just as a placeholder. And then inside that placeholder, in place of the x, I'm going to be plugging in my g of x, which is x plus 1 over 3. And now I just need to simplify. All right, so I've got 3 over 1 on the outside, so I can cancel my 3's. And now my parentheses are no longer needed because there's nothing being multiplied. So I have an x plus 1, and then I have my minus 1 back here. So 1 and negative 1 make nothing, and I'm just left with x. That's what I'm looking for. Okay, I'm looking for an x in the end. So now we're going to try it the other way around. They both have to work in order for the two to be inverses. So I'm going to plug f into g. Now if I look at g, is there any reason for me to put parentheses around this x? No, because I don't have anything that I'm multiplying here, right? It's just an x. So I'm just going to kind of leave a blank spot and put my plus 1 back here all over 3. And in that spot where the x was, I'm plugging in f. So I have 3x minus 1. And now I'm going to simplify. So my 1's cancel. And now I have 3x divided by 3, which is just x. So when you do the compositions both ways and you get an x in the end, that means that these are inverses. So I just verified that they are inverses doing this by hand. All right, but you can also do it in your calculator. So we've been doing it already, but I'm going to take it a step further and show you another little trick. So I've got my original, the inverse, my mirror. Now this looks pretty good to me, right? But I mean, still, it's just kind of hard to tell, especially when they're lines, if they're as far away from this axis over here as this one is from here. So what you can do is you can actually have your calculator draw the inverse of either what you have in the y1 or what you have in the y2. I always do what's in the y1 just because I'm a creature of habit, and that's what I do. So I'm going to have it draw the inverse of the blue line. Now we already know that these are inverses because we did them by hand. But when it draws the inverse of the blue line, it should draw over the red line because that would be its inverse. So I'm going to go to the Draw menu, which is right here in blue above Program. So I'm going to press Second and Program. And we want it to draw the inverse, which is option 8. All right, and then you have to tell it what you want it to draw the inverse of, which in our case is whatever's in the y1. So to get the y1 right here, you're just going to access a shortcut menu by pressing Alpha and Trace. And then you can choose from any of them. So if I did y2, it should draw over the blue line, but I always do the first one. So I'm going to tell it draw the inverse of y1, press Enter, and when you watch it, it should take that blue and draw over your red line. So that would mean that they are inverses. If it doesn't draw over the red, then they are not inverses. But this is like a foolproof way of knowing, like, yes, those are inverses. All right, so on these last two, we're just going to do them in the calculator. We won't do them by hand. So I'm going to graph the 2x plus 4, and I'm going to graph the x minus 4 over 2, and then I will tell my calculator to draw the inverse of those. All right, so I have my first one, my second one, and my mirror. So this is looking pretty good to me. All right. I also want to point out that notice that your first equation crosses the y-axis at 4, and then your second one crosses the x-axis at 4, right? It's inverse. So I'm thinking, you know, this should be good. But I'm going to go ahead and have my calculator draw the inverse of the blue equation, which is the very first one I put in. So I'm going to go to the Draw menu, Second Program, and I'm going to say Draw the inverse, which is option 8. And then I'm going to tell it I want you to draw the inverse of y1. So I'm going to go to Alpha, Trace, and I'm just going to choose y1 and then press Enter. And notice it drew over your red line, correct? So these two are inverses. This would be yes, I have confirmed. All right. And I do want to point this out. Once you actually have that in your calculator one time, you can just go up and press Enter on that and then just reuse it instead of going through the whole process. My suggestion is, though, to practice doing it. That way, you know at least how to get it on there at one time when you test. All right, so we're going to plug the f of x into ry1 and the g of x in ry2. It doesn't really matter which one you put where, just as long as they are in separate ones. Now, I did not put the parentheses around this base because it's taking the base, the whole base, to that power. Now, if I was on like a TI-83, I would definitely need to be putting parentheses around this and my exponent as well. But in this case, they're not needed. All right, so this one is really not looking that hot to me. I'm thinking this is going to be a no, but I'm going to go ahead and verify. This is kind of swooping upward, and I don't even know what this is doing. So I'm going to go ahead and have it draw the inverse. So second program, and then we're going to choose draw inverse, which is 8. Oh, and I've got like a ton of stuff in there. Let me do that again. And then we're going to put in the y1. So alpha, trace, choose y1. All right, and notice that did not draw over my red line, right? So these are not inverses. All right, I'm going to actually add a problem in here. So f of x is equal to 2 over x minus 4 plus 7. Now, we have done problems like this before, but I feel like a refresher is a good idea. So we're going to switch our x and our y. Oops, I'm going to actually need to switch here. So x is equal to 2 over y minus 4 plus 7. So I think that, we wouldn't get mixed up on this. We all know we need to take away the 7. So that gives me x minus 7 is equal to 2 over y minus 4. But we might get confused about where we should go from here. Well, you're solving for y, and you can't solve for y if it's in a denominator. So since I am dividing by this whole thing, I need to multiply by that whole thing to get it off of the bottom. Now, there are two things over here, so I have to put parentheses around that to show that I'm going to be multiplying another binomial over here. So now I have y minus 4 times x minus 7 equals 2. Now, you might have the instinct to try and distribute this, but if you do that, then you're going to get a y times an x and then a y times a 7, and then it's just going to be a big nasty mess. You just want to solve for y. Well, y is in this parenthesis, and what's hindering me from accessing that is that I'm multiplying it times the x minus 7. So I need to divide by the x minus 7. Now, since there's nothing with that other than the x minus 7, I don't need parentheses there. And I don't need parentheses here because I've gotten rid of what I was multiplying by. So y minus 4 is equal to 2 over x minus 7. And then from here, I think that you would have it. You would just need to add your 4. So f inverse of x is equal to 2 over x minus 7 plus 4.